Hello everyone and Bismillah. In this video, we are going to design a proportional controller that leads this given transfer function of a plant, of a physical plant, to follow the given reference with this certain specification, which is the rise time of that following process should be less than or equal to 0.5 seconds. Now, the first thing that has to come to your mind in such a situation is in order to get the most out of the controller that we are going to design, we have to think of a closed loop configuration, closed loop control configuration, in which the controller is cascaded with the plant. So let's just do that. Now we have the controller block as maybe C, and it's actually cascaded with the plant itself, which is P. Then we are taking our output from this block. However, we need also to add the reference itself, which is R. We also add this block because as we said before, we want to form a closed loop configuration. So we will be taking measurements from the output and feeding them back to the summation block. And this summation block gives us and forms the error between the reference and the output. So in here, we will be having the error. The error between the reference and the output will be the input of the controller block. Then the controller will output the control signal, which is U, and this U will be entering P, and P will be outputting Y. Now, after doing this, we have to form the transfer function of this closed loop system. Any one of you who has taken any simple, control course would be able to form that transfer function. Let's just call it H of S. So H of S is equal to, simply since this is a minus or negative feedback system, it will be something like CP over 1 plus CP. Now, this can be written as let me just spare some maybe area. Yeah, so this can be written as, now we know P, this is P, it's given to us. However, we do not know about the controller, except that it's gonna be a proportional controller. So this is very important. It's a very important information. And by proportional controller, we mean a constant. It's simply a constant. So let's just call it KP, K sub P. So this will be something like this. So the controller itself is actually K sub P, and the transfer function of the plant is given in here. It's S plus 1 times S plus 2. Then we will do the same for the denominator. It's Kp over S plus 1 times S plus 2. Now we have to simplify this transfer function. We will simplify it by multiplying both the denominator and the numerator by this quantity. And yeah, let's just, this quantity is simply, this quantity can be simply written as S squared plus, I guess it's 3S plus 2. Yeah. So we will multiply both numerator and denominator by this quantity. This will give us H of S is equal to Kp, cancellation will happen, and this is over S squared plus 3S plus 2 plus Kp. Now, when this comes to your mind, okay, you may think of the standard transfer function of a second order control system. And this standard transfer function is written as omega n squared over S squared plus 2 times zeta times omega n times S plus omega n squared. So this is the standard transfer function of any kind of a second order control system. Why am I writing this in here? You will be seeing that in order to achieve this specification of the rise time, we will be benefiting from this standard transfer function. Now we know that in control systems we pay a lot of attention to the characteristic equation of a system, and the characteristic equation of our system is actually S squared plus 3S plus 2 plus Kp, and it's also equal to S squared plus 2 zeta plus omega n plus S plus omega n squared. Now, let's say that we want to achieve this specification. Now, there are some approximations in the reference books, of control engineering, continuous control engineering, and so on. And we will be using one of them in order to determine omega n. So omega n is approximated to be 1.8 over TR. Now, TR is actually the rise time of the system. So we may say that TR is almost equal to 1.8 over omega n, and you know that the TR, the rise time of our system, is needed to be less than 0.5. So we may write that 1.8 over omega n, which is almost TR, should be less than or equal to 0.5. And this can give us that omega n should be greater than or equal to simply, I mean, I'm skipping some calculations, so it should be greater than or equal to 3.6 radian over seconds. So this is very important. We have got a result in here, and we will be applying this result to our controller. Now let's go on and try to continue finding the other things in our characteristic equation. So now we have the characteristic equation to be s squared plus 2 zeta omega n s plus omega n squared. And we know a lot of things now about this characteristic equation. We know omega n, which is the most important thing. So we will be rewriting it as s squared plus, let's say, 2 zeta times 3.6. Now you may see that I selected 3.6 to be omega n, because the condition that we had is for omega n to be either greater than or equal to 3.6. So I may say that our omega n is selected to be 3.6, 6 radian per second. So this is a matter of choice. I may select omega n as I want. It's not a problem. So now this is, sorry, this was times s, then plus 3.6 squared. Now, from here, we are going to benefit what we have got as from our transfer function. I mean, this is the transfer function of any standard second order control system. But our transfer function of our control system is this. This is our transfer function. So by coefficient matching, we will be benefiting from the combination of those two transfer functions. Now, this means that I will say that for zeta to be found, we will say that, I mean, in our transfer function, we have all these coefficients as what? We have them as 3. So we will say that zeta should be equal to 3 over 2 times 3.6, because this is what we have found. And this is actually equal to, I mean, it's almost equal to 0.417. So now we have found omega n. We have also found zeta of our system. Now we know the undamped natural frequency of our system. We know also our damping ratio of our system. This is very good. We need to find the appropriate KP, the controller that we are desiring to design. So KP, I mean, from our transfer function, we may see that KP plus, where is it? It's here. KP plus 2 should be equal to omega n squared. KP plus 2 is equal to omega n squared. So let's go back and write this down. So KP plus 2 should be equal to 3.6 squared, okay? Which is equal to, I mean, I think it's 12.96 from my calculator. So we will be saying that KP is equal to 10.96. Now we have found everything in our system. We have found the suitable controller that achieves the needed rise time in our system. And now we can write our transfer function as h of s is equal to KP, which is 10.96, or is it? Yeah, over s squared plus 3s plus 12.96. So this is our closed loop transfer function. We have found it, and we may also go back to here, and actually we'll be doing this in Simulink in the next video. So this proportional controller in here will be simply replaced by 10.96. Well, thank you for listening to this video, and in the next video we are going to simulate what we have done, and we are going to check if this thing is actually working.